Engineer Sips today. Hope you had a good couple of days, and I hope you are ready to continue with Arduino, because that's what we're going to do. We're actually going to build our first circuit today, and that's also going to be sort of a tutorial for working circuits.io and how to do stuff in it and everything like that. So we'll be going over a decent amount of stuff today, nothing too crazy. Anyway, yeah, just a review for what we did on Monday. We started talking about Arduino, what it is, what it can do, and I got, sort of a really long tangent about that. But we explored all that, and it was, take it how you will, either you found it interesting or not, or you found it really, really cool and you want to continue with it, in which case, cool. That's exactly what we're going to be doing now. So, without further ado, let me go ahead and get circuits.io open so we can get started on this business. And you guys can go ahead and go to that site as well and log in with your information if it hasn't already saved your login and all that stuff. I'll give everybody a moment just in case it didn't automatically log you in. Okay, so presumably everybody should be logged in now. We're going to go ahead and create a new circuit. So what I'm going to have you do is I'm going to go up here to sort of the middle top. There's one labeled Create. I'm going to click on that one. We're going to be presented with a few options here: Electronics Lab, PCB Design and Manufacturing, and Circuit Scribe. We are going to be interested in the Electronics Lab. So go ahead and click on the green button that says Open Electronics Lab Hub. You'll be taken to the Electronics Lab Hub, unsurprisingly. Like, that really shouldn't be a surprise. So once you've done that, go ahead and click on New Electronics Lab. And it'll spend some time thinking and thinking and thinking and loading and thinking and loading and thinking. I recommend you do this on Chrome because I do know it works on Chrome. If you don't have Chrome available, though, you're more than welcome to try it out in your browser of choice. If it's not working, that would be my first avenue, is to try out Chrome. If you're trying out Chrome and it's not working, it might make sure there's no plugin being blocked from starting up, and the page is fully loading and everything like that. But once it's done loading, you should be looking at this. Does anybody know offhand what this is? You guys probably, most of you probably know, but just, as a question. Yeah, you got it, Jacob. So do Jean-Marc. It's a breadboard. No surprise there. You got that as well, Jacob. Other Jacob, both Jacobs got it. Yep, you got it too, Noah. Somehow you can't sign into this. Is it giving you an error message, or? What's it doing? It removes everything you typed in. Interesting. Like if you type everything in and then you click login, it just blanks out everything you typed in, and you don't get like an error message or anything. Huh. Let me see here. Oh, what browser are you using, Treelook? There might be some strangeness with a redirect. Let me see. Oh, did you not have a... Gotcha. Just see if you can't... see if you can't get that verified. Also, try getting it to work on Chrome if you can. If neither of those work, maybe we can explore what we can do at the end. In the meantime, though, you can just follow along with... it says they need an Autodesk account. They shouldn't need one. They should just need to verify your email address. Yeah, it's another thing you can do. You can put in your date of birth so that you're, like, create a new account, put in your date of birth so that you're 21, and then just skip that altogether. Not something I normally recommend you guys to do, but sometimes in situations like these, when they click the verify link, it sends them to the Autodesk webpage. Huh. Well, I mean, you can download it and it's free. It's worth a try. Um, yeah, well, we can explore that maybe closer to the end of class before I go off to my other class. I guess in the meantime, you can get the download started and then just follow along with what we're doing here. Yeah. Okay, so yeah, breadboard. That's what we've been looking at. It's an exciting breadboard. It's got holes in it, arranged in rows and columns, and there's blocks of holes. There's a lot of them. What exactly are we looking at here? Well, if you're not familiar with how a breadboard works, just in case you aren't, I imagine that many of you probably are, but not everybody is. A breadboard is an easy way to rapidly prototype circuits. Essentially, if you've ever looked at like an actual circuit board, it looks pretty crazy, right? Like it's got all this kind of stuff going on. Well, these are connections. These are electrical connections made from one area to another. And these connections generally connect to holes where stuff gets soldered into. And as an example here, this integrated circuit has been soldered into a circuit board. And as you can see, there's connections which go off of the integrated circuit and lead to other places on the circuit board. This is fantastic for basically stability and longevity. The connections are very stable. The soldering is a very long-lasting way to get something to stay connected and conducting electricity along the lines. And yeah, whoever did the soldering here, it was probably a machine. but it's a very, yeah, it's very nice work. Anyway, this kind of stuff is built to last, which is great once you have a finalized circuit. However, it's not so great if you're trying to build a circuit and you're not entirely sure how everything's going to be laid out. You know, if your concept is correct, that kind of thing. You can put it down on paper and it'll probably be fine, but sometimes, you know, unexpected things happen with your math and stuff like that. And it's always good to double check and make sure before you go and build something like this for, like, you know, mass production or whatever. So that's where a breadboard comes in for certainly a preliminary thing, and definitely for home projects and stuff like that if you want to test something out. A breadboard is very simple. Stuff just plugs into the holes on the breadboard, whether they be LEDs or integrated circuits or resistors or diodes or whatever. You just plug the legs of the component into the holes on the breadboard. Same thing goes for jumper cables. Now here's where the advantage of a breadboard comes. Well, one of the interesting things about a breadboard, rather. So you'll notice if I mouse over these columns and these rows, we get, if you do the same at home, you get a green line which connects everything in that column or in that row. And you might notice on the two rails on the end, those are actually very long green lines, whereas all of the rails in the middle, they're much shorter green lines. They're, you know, just the single block of connections right there. On a breadboard in real life, those holes that are denoted by the green line are all connected to one another inside of the breadboard. Like if we were to do breadboard, not breadboard, cutaway, you can actually see it here. This is like looking underneath the top of the breadboard. You've got these silver sort of metallic things. These are the rails on this. You can imagine like one of those silver metallic things underneath, and that conducts electricity. So everything plugged into a hole on the same row is all connected to one another inside of the breadboard. So it allows you to connect multiple things together without having to do all kinds of weird, crazy, like sticking multiple things into the same hole kind of madness. And the fact that there are so many of them and they're only aligned, in this case, because I had the breadboard rotated this way vertically, means that you can plug components, you can jump rails and then plug other components, and that's how you connect things together. Now, the plus and minus ones are super long. You probably noticed, plus and minus rails. That's because commonly, with a lot of circuits, you're going to have a common ground and a common power. And everything that needs power is going to be hooked up to that common power, and everything that needs grounding is going to be hooked up to that common ground. Great. That's my first Lenny face. Anyway, no, don't flood the chat. Kappa. You need a common ground, you need a common power in order to ensure like a clean circuit, and also to basically make sure that you're receiving the same power along all lines. So that's the main advantage of that kind of thing, and we'll actually utilize the common ground and the common power when we're building circuits. But that's what those are for. Now, as far as controlling 123D circuit is concerned, or circuits.io, I suppose, I apologize, you can use the mouse wheel to zoom in and out, to no one's surprise. Left-clicking once will select something. Left-clicking and dragging will move it around. Right-clicking doesn't really do anything, so don't worry about it. Having something selected, so having this blue line around outlining it, so having it selected and hitting R will rotate it. Holding down Shift and then hitting R while it's selected will rotate it in the other direction. rotate, 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 rotate. You get the idea. I'm going to keep it vertical now, vertically aligned. Clicking in the mouse wheel and moving your mouse around will pan it. You can also do this by clicking and holding with the left click. So clicking and holding left click with nothing selected will also pan it around. Make sure that you're not just moving something around. Make sure nothing has the blue outline when you're doing this, and you'll be able to pan. Now, we just have a breadboard. Not that exciting. Not much we can do with that. We need to bring in some other stuff that will do cool things. So that's exactly what we're going to do. Over here in the upper right-hand side, you're going to have a whole bunch of symbols. We're going to ignore those symbols for now, although they correspond to like schematics and PCBs and stuff like that, as well as help and settings in your login. But we are going to worry about the three buttons that are just below that, the one labeled Code Editor, the one labeled Components, and the one labeled Start Simulation. We're very interested in those because we are actually going to utilize those fairly often. So here's what I'm going to do. I'm going to click on the Components button, and that's going to bring up this little tray down here. The Components tray. I kind of yelled that into the microphone. I apologize. Yeah, this isn't, unfortunately. But yeah, so Components tray. The Components tray contains like 100 bajillion million different components for use in your circuits. Not really, a bajillion million, since that isn't an actual number, but it contains a lot. We're going to use just a few today. This is going to be a nice, gentle introduction to building circuits and working with Arduino. So with that, I'm going to go ahead and I'm going to select a few components and bring them out. First one is going to be the resistor, because most circuits, if not all circuits, pretty much all circuits need a resistor. So I'm going to go ahead and click and drag this resistor out, and bam. Just by clicking and dragging onto the I guess workspace, we've added a resistor to our circuit. We haven't connected it to anything, but it's part of a circuit. I'm also going to drag out an LED. You have to do a little bit. Hello, there we go. LED, go away. You can make things go away by selecting them and hitting the delete or the backspace key. Bring back the components tray. Okay, so we need one more thing. It's kind of important. Anybody guess what it is? Okay, power. I like that. That's a battery is not quite a battery, although I like the fact that you guys are thinking power. This is actually going to be our power source for this circuit. You are correct. However, it's not going to be a battery, and it's not going to be a wire either. Yeah, you got it, Jean-Marc. It's going to be an Arduino. We need an Arduino. It's kind of an important part of this whole circuit. The Arduino is going to supply power as well as be the logic brain for our circuit. But in order to use it, we need to have one connected to the circuit. So I'm going to go ahead and I'm going to add one. Yeah, Uno R3. Now, it's going to be part of our components tray, and it's going to be somewhere listed in all this stuff. But like I said, there's like a whole bunch of stuff. So the easiest way is in the upper right part of the component tray. So realistically, it's going to be somewhere in like the bottom third of your screen on the right. There is a search bar. Whoopsie. And we're going to search for Arduino. Wow. Excuse me, fingers aren't cooperating. There we go, Arduino. And we're going to get three results. We're going to get Arduino Uno R3, DF Arduino R3, and Arduino Micro. We are going to use the Arduino Uno Mark III. Just go ahead and drag that out. Now this thing is decently big, certainly relative to our resistor and our LED. Everything's meant to be more or less to scale, so this would be more or less to scale to how you would like to physical components and stuff like that. Now, again, this all follows the same rules, so I can select the Arduino, I can rotate it with R, which is actually exactly what I'm going to do. I can move the resistor, rotate it with R. I'm going to keep it like that though, put it right there. I can also rotate the LED, it looks super silly. Now, adding a component to the circuit is really simple. I'm just going to drag this LED up here, and as you can see, it snaps to one of these holes. There's going to be, at least in the case of the LED, there's going to be a hole with a square, and there's going to be a hole without a square. And that corresponds to the cathode and the anode. Basically, the positive and the negative parts of the LED. Now I plugged it in. Can anybody tell me what's wrong with how I plugged this in? Yep, you got it. Both of the leads are on the same row. Power, we need more power. There's that too, definitely. But if we had this whole thing hooked up to power, the major issue we'd have right now is this LED, both of its leads are plugged in on the same row. Which means, okay, so let's say we hooked up our circuit. We had something running from, here, and then the resistor was over here, or whatever. Ideally, our circuit would run through, up the LED, back down, light up the LED, over the resistor, and out, or, vice versa. Realistically, what's going to happen, because it's on the same rail, is electricity. Well, electricity is lazy, first of all, as I'm sure you guys know. You've always heard, like, travel the path of least resistance. Electricity literally does that. It travels down the path of least resistance. Like, this is not some sort of allegory or anything. Wherever the resistance is lowest, you're going to have more electricity travel down that way, if not all of it. In this case, because there's essentially, there goes my neighbor. In our hypothetical situation, let me choose a different color for this now. I'm choosing all of the ugly colors so that I can distinguish one another from them. In our hypothetical situation, the power would travel to the LED, up to the LED, back down, and it would have two choices. You could either go along this and slow down and, hit the resistor, and, it wouldn't be able to go as fast, or it can shoot right back this way, up the LED again, back down, and then just continue the circuit over and 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 over again. Well, not forever, because there is going to be a point where you're going to basically have too much power going through the LED, and you might be able to guess what happens next. It's true, it's not a superconductor. Give you a hint with a sound effect. Hey, no worries, Matthew. Do what you got to do. The video will be up on YouTube later tonight, certainly by early tomorrow morning, and then you can always watch it to catch up. It will explode and set your hair on fire. How are you drawing on the screen? Oh, it's a function of GoToWebinar. I guess it's one of the presenter tools. But yeah, so basically, bad stuff happens. The LED pops. It goes. Magic blue smoke comes out. You've let out the magic blue smoke, which makes the component run, and potentially, if you're not careful and you have flammable things close to it, you might have a small fire on your hands. Which we've accidentally done before. So don't make the same mistake. Anyway, so that's what's wrong with this. In order to fix this, super easy. Select, press all the wrong buttons, select, rotate, reseat, done. Now it's on two separate rails, and you won't run into that issue. Now that we've done that, let's go ahead and bring our resistor over. Now you might be asking at this point, what are you building? And that's an excellent question. What am I building? What's the point of all of this? Let's go back. The whole idea is we are going to build an LED that blinks. I mean, we're not going to build the LED. We're going to build an LED circuit that causes the LED to blink using the Arduino. Super exciting. I know, super exciting. But, you know, all of this kind of stuff has to start somewhere. This is kind of like the hello world of Arduino programming. Let me see if I can't bring up the circuit. Here we go. This is kind of like what our end result is going to look like. We're going to have our pin 13 plugged into the anode of the LED. The cathode into the cathode. The anode is going to be plugged into the resistor, and then the resistor is going to be plugged into the ground on the Arduino. So that is our end goal. That's what we want to do. So far, so good, right? But how do we get those fancy schmancy jumper cables? How do we do that? Well, it's super easy, thankfully. We just left click on a hole, and as I move my mouse away, a pin slot, I suppose, as I move my mouse away, I get this nice green line that I can then right click to add corners to for no particular reason. So let's cancel that. Get this nice green line. And this nice green line denotes a jumper cable. I can connect it to something else by clicking on a pin slot when I've got the red square. And suddenly, bam! As you can see, I've got the double circle denoting that they're connected there. And, you know, we've made a connection there. So what I've done is I've made a connection from the rail that has the cathode part of the LED onto the common power, and then I have connected a jumper cable from the rail that has the end of the resistor onto the common ground. So if we were to trace a line, again in our theoretical power loop, it would go whoop, 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 up the LED, back down, jump onto the resistor, jump down, go across onto the ground. So a very simple circuit, which you probably also noticed is not connected to the Arduino yet. Why not Zoidberg? Woo! I have a horrible Zoidberg impression. But anyway, let's take a look at our components again, because there's one thing we need to double check. Resistors come in different resistances. That's sort of their thing, is they resist, they slow down the movement of electricity, for lack of a better explanation right now. They ensure that voltage and current don't get too high, of course, depending upon how you have it all set up. And they generally keep the flow of electricity sane in circuits so that you don't pop LEDs and burn out diodes and, you know, melt ICs and stuff like that. So that is the purpose of the resistor in the circuit, is to restrict the amount of power flow going through the LED. So we don't have too much. However, our components list very specifically denotes a specific kind of resistor. In this case, a 330 ohm resistor. That's what that omega symbol means as far as resistors are concerned, is ohms. Ohms measure how good a resistor is at resisting stuff. Basically, the more ohms it has, the higher the ohm value, the stronger the resistor is, the more it will resist, and you know, the more it converts electricity into heat, because that's kind of how it resists, is it just turns electricity into heat. But the more efficient that conversion is, I suppose, or the less efficient. Because if it was more efficient, you'd be generating a lot of heat with very little amount of electricity. Anyway, 330 ohm resistor. But if you remember from the components tray, boop, if I were to X out that Arduino so we had a list of everything again, this is just called resistor. There's no specificity to it at all. What exactly are we looking at? Are we looking at, you know, a million ohm resistor? Are we looking at a 1 ohm resistor? Are we looking at a 550 ohm resistor? You know, what exactly are we looking at? Well, I can tell you right now that this is a 1000 ohm resistor. A, because I've done this class a couple times before, and B, also you can tell the resistance of a resistor by reading the bands on it. That is true, because resistors are generally too small to print numbers on them. So what they do is they use a sequence of 3 colored bands, and sometimes a 4th one, more often than not now a 4th one, in order to denote the quality and the resistance of a given resistor. So in this case, the colors correspond to certain numbers. Brown is 1, black is 0, and red is, I believe, 2. Yes, it's 2. And the way you read it is first significant digit, second significant digit, and then multiply it by some power of 10. Seriously, that is how you read it. So in this case, oh, you already got it blinking? Okay, so you're very familiar with this stuff. In this case, since brown is 1, the first significant digit is 1. If black is 0, the second significant digit is 0. And then we multiply it times 10, red squared. So it becomes 10 times 100, which is 1000. And that's how we know. Don't save. But how do we change the resistance of this? Oh, you got used to blink too? Nice. Since 1000 ohms is too many ohms, it's too strong. We need a lower powered resistor. Well, we can just click on it over here, the right-hand side, the upper right-hand side, we've got a properties menu where it is listed, a name is listed and a resistance is listed. And we can actually change the resistance value. So what I'm going to do is I'm going to change this to 330. I'm just going to say kilo ohms. I just want regular ohms. Select ohms from the drop-down menu. Now we've got orange, orange, brown. Orange corresponds to 3. Brown corresponds to 1. So once again, back to where we were. 3 times 10 to the 1 equals 330. Bam. So there you go. Just a small little primer on resistors there. Now I'm going to go ahead and I'm going to plug in my power and my ground to the Arduino. Power goes to pin 13. And you notice I created a breadboard wire. We actually get another properties menu for the breadboard wire, just like we do with the resistor. And in fact, with the LED, with pretty much anything, there's going to be a properties menu that appears up here in the upper right. And it's all contextual based on the things that you can change about a given jumper cable or whatever, or a given component, excuse me. In this case, you can change the color of the cable. I'm going to change this to red. I'm going to change this one to red as well. There's no particular reason why I need to do that, but it's good form because when you're working with circuits, red generally means a hot wire, whereas black generally means a ground wire. And this is something that's basically a standard. I mean, you for electronics certainly. You're going to see this in houses as well. Except the colors are going to be all messed up. White is going to be your hot wire, and depending upon how old your house is, I believe either green or black is going to be your ground wire. But obviously, if you're going to be working on stuff in your house, I would highly recommend you look this stuff up on the internet first and don't take my word for it, because I've been wrong in the past. It's not unheard of. I've been very wrong. So don't just be like, oh yeah, Mr. DeToy from that one class 10 years ago said that black wire is the ground wire, so this is totally safe to touch. And then, you know, bad things happen. Because 120 volts is much more painful than 5. Simple mathematics. Simple geometry. Anyway. I'm going to go ahead. Simple logic. Now that we've got this all plugged in, this is actually our complete circuit. Not too bad, right? Like, it's just kind of like a couple of wires and boom. In fact, I could have skipped over the whole common ground and common power thing and just plugged them directly into here, which is totally doable as well, except, you know, I just kind of wanted to start that habit. It's kind of a scale of pain in volts, and it's kind of a scale in uh, I guess fatality and amps. um, Volts hurt, amps kill. Really, I mean, it all hurts. Being electrocuted is not fun, but yeah. And to say that volts hurt, amps kill is a little bit disingenuous because they are somewhat related. Um, you're not going to have a terribly high amperage without a decent amount of voltage. And, you know, so there's that. Anyway, this is our electrical circuit. Like I said, we didn't need to have the common power, common ground. This is simple enough that we didn't need it. But we're going to go ahead and start doing this anyway, so it's not going to be all kind of like, what are you doing whenever we start building more complex circuits? Now let's go over to the software side of things, the actual coding bits, because that's what we need to do with our Arduino. Now, you might have noticed if you clicked on Code Editor up here in the upper right-hand side, that the Arduino comes preloaded with code. In fact, this is the code that you need in order to get the LED to blink. This is all of it right here. This is the blink code. But what we're actually going to do is we're going to delete all of this and we're going to type it up from scratch because I like making your guys' life hard. Also because it's a good way to sort of go over what everything does. And we're going to do that fairly quickly. I apologize because I didn't realize that we had 15 minutes left. No problem. I live to serve. So any given Arduino program has two main parts that are always a part of an Arduino program no matter what. There can be other stuff built up and around this stuff. There can be other things that talk to this stuff. There can be stuff that you write yourself that will interact with these things. But they always have to be there. Always. I don't know if I drove that point home enough, so I'm going to say it one more time. Always. They're called, I'm going to type this on Notepad so it's bigger. Setup and loop. Now you might notice there's extra punctuation, there's extra words. So in fact, if we were to read this, it would be void setup, open and close parentheses, open and close curly brackets, and void loop, open and close parentheses, open and close curly brackets. But all that stuff right now is sort of part of the structure. Right now, we're interested in understanding that there needs to be a setup function and there needs to be a loop function. And that's what these are. These are functions. These are blocks of code that can be repeated. Because the way an Arduino handles itself, the way an Arduino runs, is you turn it on, right? And it starts to basically load the program that you've written it into the registers in the CPU. Fancy terms, don't worry about it for now. Void setup is always going to be the first thing that runs whenever an Arduino first gains power and first starts running its program. It's always going to be void setup. And void setup is always going to run once. Setup is where you set up everything that you need for your program to work, predictably. It's kind of why it's called setup. Now void loop loops. No surprise there, right? But here's the thing, it loops forever. It loops as long as there is power in this Arduino, and as long as it's already run setup once, it's going to run void loop forever. And that's how you can keep an Arduino doing this same thing over and over again, keeping an eye out for the temperature to dip below a certain point before it starts turning the heater on, looking for I don't know, keep checking the time of day before it turns on some lights. Check for the state of a variable so that I can change the color of some LEDs. look for a signal from wireless adapters so that it can activate a servo, whatever it's doing. In this case, it's going to be sending an on and off signal to an LED forever and ever. But we've got some other stuff we're gonna have to do first. So make sure you've got your void setup and your void loop. Also make sure that your void setup and your void loop have void and then a space. They have the open and close parentheses without a space. And they have the open and close curly brackets. Now the open and close curly brackets, here's the wacky thing about them. I can put them down onto the next line. I can separate them like that. Everything's still okay. Well, why is that? Well, the curly brackets denote the beginning and end of a function. In this case, void setup is going to have at least one command in it. But how many of you have messed around with like Python before? You know how in Python indentation is super important? Like if you want something to be part of a loop, you have to put something down on the next line and indent it further past that loop declaration. Maybe, potentially, possibly. Well, if you have, it's the same basic idea here. Think back to the to Scratch last week, and when we created that loop, and how the loop had sort of that big block which wrapped around all the other blocks. You can think of these curly brackets like that big block wrapping around all the other blocks. This is denoting the beginning and end of that big block. Any other commands we write inside of these curly brackets are going to be like the other commands that are inside of that big loop block. Wow, big loop block. Jeez. Big loop block in Scratch. Whew. Okay. So functions, those are a thing. Before we mess around with functions at all, though, I'm going to add one thing. This is our first command in programming. int space LED capital PIN space equals space 13 and then a semicolon. The semicolon is not a typo. Semicolon is kind of like the period at the end of the sentence. Anytime there is a command, an explicit command given in the Arduino programming language, you put a semicolon at the end. Notice how there's no semicolon at the end of void setup or void loop. That's just because they're not actual commands yet. They're going to be commands inside of it, but they aren't commands. But yes, the semicolon is very important. If you run into an issue with your code, probably one of the first things you should double check and make sure is that you have semicolons where they're supposed to be and no extra semicolons where there aren't supposed to be any. What exactly is happening on this line? int, that's short for integer, actually. I was going to have you guys guess at it, but I'm just going to go ahead and say it. It's short for integer. Integer space LED pin equals 13. We've declared a variable here and we've given it a value. A variable is just a spot in memory that holds information. Like the computer says, here is where I want to put all this stuff. You say, hey computer, reserve some spot in memory to hold information. And it goes, okay, I will. And you go, okay, I'm going to call it LED pin. And it goes, okay, so I know now that anytime you're talking about LED pin, I know you're talking about this variable. And you go, uh-huh, and I want it to be able to only hold whole numbers, hence the integer. And it goes, okay, it can only hold whole numbers. All right, excellent. And then you go, okay, so now you know where this is. You know what I'm talking about in the future when I refer to it. You know it only holds whole numbers. I'm going to tell you to have it hold 13. And it's going to go, okay, so I'm going to take that spot and I'm going to put 13 in there. Got it. Excellent. Cool. So now if we use LED pin later, we can just use the word LED pin. And in essence, it's like we're referring to the number 13. This is the same thing as writing the number 13 right now. Now the power of variables comes in with the ability to change that value on the fly and do math to it and stuff like that and send other places. But for now, think of it like you're just referring to the number 13 with a fancy name. So now that we've done that, let's go ahead and stick our first command inside of void setup. This is going to be this whole mess right here. Pin mode, LED pin, output. Notice how the M in mode is capitalized. Notice how we've got pin mode, no space, open parentheses, no space, LED pin, just like we have it up here, comma, I put a space here, you don't have to put a space, and then output, all capitalized, closing parentheses, semicolon. What exactly is going on here? Well, pin mode is, well, it's function and needs some information. It needs some information from us. It needs what pin we're setting the mode for and whether or not we're setting that pin to input or output. It just has to be lead. I gotcha. That took me a second. Anyway, so with this one command, what we're doing is we're saying, hey, pin 13, set it to be an output pin. So it's going to send electricity out. It's not going to be waiting for a signal in. It's going to be sending a signal out. And that's exactly what we're interested in right now. Pin 13, we want to send electricity out so that it can light up the LED. And that's the only thing we're going to put in void setup, believe it or not. Because in void loop, that's where all the magic is going to happen. We're going to say digital write LED pin high. Digital write is a fancy name for send a signal out. Either a high or a low signal, an on or an off signal. That's all digital write means. So digital write with a capital W, digital write, opening parentheses, LED pin, comma, high, all capitalized. High is all capitalized, and closing parentheses, then semicolon. So what this line is essentially saying here is digital write, send a signal out on LED pin, turn it on. Now we're going to say, not my last name, delay 1000, digital write LED pin low delay 1000. So delay is simply waits. And the reason why it's delay 1000 is because an Arduino can measure time in thousandths of a second. So if we're waiting 1000 thousandths of a second, we are waiting 1 full second. If we brought this down to 500, which I am in fact going to do for the purposes of showing the blink faster, it'll wait half a second. And then we have to say digital write LED pin low. And that's just because computers are dumb. Like we have to tell the Arduino to turn the LED back off. We can't just assume that if we say digital write LED pin high, delay 500, it's going to have the LED be on for half a second, and then it's going to automatically turn off. It's not going to happen. All it's going to do is it's going to turn the LED pin on, and then it's going to wait half a second, and then it's going to go back to the top of void loop, and it's going to turn the LED pin on again, which it's already on, so it's just not going to do anything. Then it's going to delay half a second. Then it's going to go back to the top of void loop. Then you get the idea. So we have to turn it off. And we have to delay another half second so we can actually see the LED turn off. Now with that in mind, that's actually all of our code. So I'm going to go ahead and copy paste that from our I'm going to copy paste it from my notepad into the code editor for the Arduino. I'm going to hit upload and run. Now, as we can see, the L pin, which corresponds to pin 13, that's blinking exactly how it's supposed to be. The LED, however, is not. And that's just because I'm a dingus and I put it in backwards. So let me just go ahead and stop simulating. I'm going to bring out the LED and rotate it 180 degrees and plug it right back in. So now when we start the simulation, the LED is blinking. Hooray! Huzzah! We have a blinking LED. And it only took an entire hour. We did it. We did it, class. Anyway, it's 7:53 now. I know I kind of rushed that in there, but I wanted to make sure we got the poll questions in and I was able to help you guys out by answering questions before I had to go to my high school class. So let's go ahead and without further ado, let's ask the first poll question.